This video is a review of the properties of a common emitter amplifier. Just to remind you, what makes this a common emitter amplifier is two things. From an AC standpoint, the emitter is attached to common. And so when we're measuring V out, it's with reference to common, which is the voltage from an AC standpoint of the emitter of the transistor. And also one of the ways to tell what kind of amplifier is by looking at where the output signal is taken. And in the case of a common emitter, the output signal is actually taken from the collector side of the transistor. Now, the first thing to understand is how to write down the AC equivalent of this amplifier. It's an important skill to at least understand and think about before you work on amplifier problems. So the first thing to point out is that we have in this particular schematic a divider, a resistive divider bias, and the voltage at the base is set to some finite non-zero value. But when we bring the signal in, we want to bring in the signal referenced to ground, and so we put this capacitive coupling in between. And similarly, we have a capacitor on the output to read out the output voltage. But from an AC standpoint, all of these capacitors, this one, this bypass capacitor, and the output capacitor are all basically shorts. So from an AC standpoint, the first thing we can do is short out everything that has a capacitor in it. Oh, and this is VCC plus. Oh, no, it's not VCC plus anymore. I purposefully left that out. Because the next step is we're going to realize that any constant voltage in AC equivalent is equivalent to ground. So the top voltage, which is VCC plus in DC, is equivalent to AC ground. So this point is tied to AC ground. Now, since this resistor is connected to AC ground and this resistor is connected to ground, these are both parallel to each other. So we rewrite the diagram this way, with R1 and R2 both going to ground and parallel to each other. And then the other thing that we do is we write out the equivalent of the transistor, which is a very small resistance, R sub E, which is approximately 3 ohms. And there is a current source that is proportional to the base current. So this current source is equal to beta IB. And then we've got a resistor on the collector side, which we'll call RC, and V out is being measured with respect to the voltage drop across RC. Now, the last thing we can do when we're simplifying this is we can just draw the current source and then bend this wire and draw RC relative to ground and V out across this, okay? So now, if we want to understand what the voltage gain is, well, let's take a look. So what is the definition of voltage gain? Voltage gain is V out over V in. Well, V out is simply the current, the collector current IC going through the collector resistor RC. And so that's going to be IC/RC divided by V in. And one of the things you'll notice is V in, these are all parallel to each other. So V in has to be equal to the voltage across RE prime, which is just IC times RE prime, and you can see that the ICs cancel out. Now in reality, this is actually IE, the emitter current, but we're approximating IE as being very close to IC, okay? And so what we end up getting is that the voltage gain is equal to the ratio of the collector resistor to R sub E, and since R sub E is small, 3 ohms, if this was like, let's say, 10 kilo ohms, we have a very, very large gain of, 10,000 divided by 3, for example, in that case. Now, you'll notice that in this particular situation, there are two things that are true. The first thing is that there is no other resistance except for the effective resistance of the transistor itself, and also there's no load on this circuit, and we're going to look at both of those cases. The first thing that I want to talk about is what's called swamping. And swamping is where you actually purposefully put a resistor, even in the AC equivalent, in series with RE prime. Now, if you do that and you do the math, you get that the voltage gain is just equal to RC divided by the effective resistance of both of these resistors combined. And since RE is likely quite a bit larger than RE prime, you get that it's equal to RC divided by RE. Now, what does this do? Why would we want to swamp? Well, RE is a very, very sensitive resistance value. It depends highly on temperature. And from resistor to resistor, yields are not very uniform. So you might have one resistor with a resistance of 2.5 ohms effectively, one with a resistance of 3.5 ohms. And if you take a large number divided by a small number that's moving around by a lot, you get a fairly unstable gain. So depending on the particular resistor you use and particular environmental conditions like temperature, the gain can vary a lot. What swamping does is it lowers the gain because RE becomes bigger, but the gain is now defined more by the value of some resistor that you purchase, and you can purchase resistors that are very stable and reproducible, so you're trading lower gain for more stable and reproducible gain. Okay, so that is the swamping situation. Now, what about a loaded common emitter amplifier? Well, if we have this configuration, but now we add R sub L, well, easy enough to calculate the gain. The gain is going to be the resistance of both of these together, which are parallel to the resistance RE prime. So it looks like this: RC parallel to RL. Now, the last thing I want to talk about, which we didn't spend a lot of time in class, and for review purposes I wanted to go over, is the equivalent impedance. And first we'll do the input impedance. Now, the input impedance, in other words, the resistance seen by this power source, is going to be equal to the effective impedance of the base of the resistor, and that's going to be in parallel with R1 and R2. Now, the parallel combination with R1 and R2 is fairly obvious. But now, what is the impedance of Zn? So Zn is equal to Re times beta plus 1. And the reason for this factor here is that whatever current this voltage supply pushes through the transistor is going to be multiplied by this factor of beta plus 1 going through R sub E, and that's going to basically effectively amplify the resistance. Whenever you have a resistor that's on the other side of a transistor, this side of the transistor sees that resistance multiplied by the large factor that the current is multiplied by. And so that's Zn base. So if you take that and put that in parallel with R1 and R2, that is your input impedance. And the output impedance is fairly straightforward. It's just your collector resistor in parallel with your load resistor, the parallel combination of the two. And of course, if you have a swamp resistor, Z in base is going to be beta plus 1 Re prime plus capital Re, where capital Re is the swamp resistance that you put in series with the emitter.